All right, so here we go. Computer science. What is it?
It's science of the computer.
I'm not even going to write that on the board. I'm objecting
It's coding.
to that particular. Okay, coding. That's a good part. Okay, yep, coding.
Fixing computers?
Repair.
Yeah.
I'm not going to say computers. I'm going to say electronics. How about that?
About like research or like
Research. How come computers today are faster than they were 5, 10, 15, 20 years ago?
technology.
Yep. Tech, research.
Isn't computer science mostly software side?
There's software, sure. We'll also call this apps. It was always software before, but now there's apps. Devices seem to have apps, not software. What the difference is, I don't know.
Would it teach us how to break into the most like secure?
So I'm going to use a term here on the board that we don't really know what it is yet, but InfoSec is what that's called. What does that stand for?
Information security.
Information security. I think that's kind of what you're talking about, right?
Yeah.
Is all the hacking and the breaking into systems and the ransomware and all sorts of things. Yes, InfoSec is a thing. You know, there's another thing that's kind of attached to this also. CRYPTOGRAPHY is how I'm going to spell it. Cryptography. What is that?
Encoding.
What do you mean encoding?
Oh, we did it out
Encoding data
before.
so that it's more difficult to get access to it. You're not supposed to have to keep
So if you want to write a love note to that cute girl in class, but you don't want to risk Clymer catching you passing the note, because what am I going to do with the note?
Read it.
I'm going to read it aloud to the class. So instead of writing it in plain English, what are you going to do with that note? Yeah, you're going to code it in some meaningful way. You're going to have a secret language with your beau that you have developed.
Wow.
So that if Clymer steals the note, it'll just be gobbledygook. Right? So that's the smart way to do it. So yeah, that's cryptography, is coding, changing the language of something so you could send a coded message. How does that relate to InfoSec?
Because you need
That's like how it does it. Sure, that's the nuts and bolts under the hood, but how are those two things related?
that stuff so that you can keep your stuff safe.
Yeah, so if I want to send my bank account information online, I don't want to do that just where anybody can read it. Right? Why you would want a bank account like 68 cents in it is kind of on you, but
just send cards anywhere. No one's going to.
yeah, I mean, just write yours down on a piece of paper for me. It's fine. I promise I won't touch your 37 cents that you have saved up in the bank. So, I might actually. The hacker would see your bank account and be like this guy could use $10 and like send you $10. So, all of these things are real. Could we stand here for the rest of the hour and keep listing things that kind of have to do with computer science?
Probably.
Probably. So we don't have time for that, so we're going to press on. But suffice to say that, yes, computer science encompasses all of these things and encompasses a lot more. And I only say that because computer science is more than any one or two or even five of these things. There's a whole realm of computer science. And when some people might think of computer science, be like, oh, I don't want to do coding. Right? I hated that when I did it in 7th grade or whatever. It's so much more than coding. Coding can be a big part of some aspects of computer science. Yes. Cryptography, I just don't get it. Like, it's complicated and there's matrices and there's crazy math involved with cryptography. Maybe that's not for you either. Or maybe it is, or whatever. So computer science is this really broad, giant field of science. And it relates to a lot of other sciences. There's physics in here. There's probably chemistry in here. There's all sorts of different things that are in the world of computer science that kind of attach to different elements of this, depending on what you're actually talking about. So And again, that's only to say that what you think of when you think of computer science, I hope it's not just that one thing that I hate about computer science, because maybe you do. But don't let that scare you away from the world of computer science, right? It's more than that. And how important is it? How important in your daily life today is computer science? Very. Why?
Because you use some kind of computer knowledge for everything.
Everything. Computers, devices, your watch, your calculator, your headphones. I mean, even like wireless headphones have computer science in them. How are the sounds just spawning into your ears? It's computer science, right? All of it kind of relates to almost everything at this point in, I don't know, in the world and today, whatever, like almost all of it relates to computer science. And again, that's kind of the opportunity of understanding the world of computer science is it's so connected to everything. Right? Like you cannot escape it if you have a firm grasp of some elements of computer science. That can open doors. Right? And I'm not telling you all to go be computer science majors, but when you go to college and you see a computer science class somewhere on the list of stuff you have to do, you know, don't necessarily fear it right off the bat. Understand that it might be an interesting thing. Don't fear computer science. So, now that we got computer science, let's talk about the language of CS. What is the language of computer science? Ones and zeros, why?
On or off?
Computers talk in binary, on or off. Why?
Simplest.
Okay, it's very simple. It's basic. How many digits do we have?
Because
2, right? Let's make it easy. Sure.
that's how electronics work when you go to the basic level. Either little resistors are either on or off.
So is that on or off? What? Is this on or off? Okay, so why? What am I influencing when I throw this switch? Electricity, right? I'm turning it off or I'm turning it on. And to the point of computers, computers can understand that very easily. Electricity is either flowing or it is not flowing. It is on or it is off, right? How many digits do we use?
A lot.
Infinity.
No. How many digits do we use? Normally, in our normal.
Oh, 1 through 10, or 1 through 9.
So how many digits do we use?
10.
How many digits do we use? All right, here we go. We got there eventually. We use 10 different digits if you include 0 as a digit, and then you get to 9. So 0 through 9 is really 10 digits. That's how many we use. So, for numbers, we use 0 through 9, right?
Yeah.
Digits. So, if we want to represent, let's do this without using numbers. 2 dozen. 2 dozen of something. In our normal representation of numbers, how would we represent that? 24. How would we write that? 2 and a 4. We're all going to agree that 24, how we use it in the decimal system, equals 2 dozen whatever. Right? While we're passing secret notes, we might as well buy her some flowers too. We'll get her 2 dozen. Carnations or something, because roses are expensive. Yeah, let's he's only got 37 cents in the bank. You're gonna want to, maybe dandelions. Maybe 2 dozen dandelions would be right for Carter. It's free. It's free. So,
Roses for my neighbor's book.
what does 24 mean? Why do we?
There are 24 of them.
Why? Okay, but what does the number mean?
It's a representation of how many there are.
Okay, sure, but
Groups of 12.
well,
Well, 2
24 ones.
you're right.
wanting,
But 24, what are we representing by writing 24?
The amount of something.
Okay, sure, but how do we break that down?
24 ones.
Do we? That's how we think about it?
1 plus 1
No,
plus
we
1 plus
think
1
of
plus
No,
2
no.
groups of 10.
Yeah, so we think of 20 and we think of 4.
Or go back to like.
Right? The tens place and the ones place. Right? That's how we use numbers. If we wanted to do a bigger number, what does this really mean? 300, 80, and 2. And if we wanted to further break this down, right, we could say, well, really, this is 3 times the 100s place, and this is 8 times the tens place, and this is 2 times the ones place. You're going to want to write this down. You're going to want to scribble this in, because this is going to help you relate to what comes next, and it's painful. It's painful. Once we get to binary, you're going to hate it.
Oh.
Now, this seems pretty easy to me, and hopefully to all of you. Why?
Fourth grade math.
This is 4th grade math, maybe even earlier. I don't recall myself, obviously it was the 1800s, but when I first learned this, it was early on. And then ever since then, we've been representing numbers this way, right? And do you think, when you're writing some number on, say, a physics exam yesterday, are you thinking of this?
No.
Of course you are. The rest of us humans in the room, the rest of us humans do not think of this. This is automatic, right? The representation of a number like 382, in our mind, we kind of have an idea what, that's the number of M&Ms in this jar, or whatever, right? And we can kind of process what this number kind of looks like or means, and we can just write this down. We don't have to think about this, right? But if I asked you to represent this number of M&Ms in binary right now, could you do it? Quickly, off the top of your head.
0, 0, 1, 0.
That's what I mean. So would you know what that is? No, definitely not. I don't know what that is, and I've majored in computer science in college, and I have no idea how to do 382 in binary. Now, could I work it out?
Yeah.
Sure. I would bet, here's the wild part, I would bet there are computer science people who could do that. Like, oh yeah, that's 101110011010. Like Sheldon on the Big Bang Theory would be able to figure this out. Right? But that's kind of the point is, now 382 is 382, duh. Representing that a different way, So let's binary. This is the fundamental language of computers. Under the hood, at the base level, at the hardware level, this is electricity on or off. And we have 2 digits that we use, where in decimal we have 10 different digits, 0 through 9. What are my 2 digits in binary? 0 and 1. 2 digits, binary. Bi meaning 2. Nary meaning nary. I have no idea what nary means. It's probably Latin for number or something. What things can we represent with 0 and 1?
I don't know.
Okay? Which one's which?
I don't know. 0 is off.
Okay?
You start saying, you're gonna see 0.
What else?
There's O.
What else could we maybe represent with something like binary? Yes and no. Which would be which?
No would be 0, yes.
What else?
0, 1.
Yeah, but we already got 0 and 1 kind of taken. What's that? True and false. Which is which?
0 is false.
Okay. Let's false. True.
Wrong and right.
Okay, so hang on. This is the one that they came up with last hour. Last hour they said right and left. What's the, why would we not want to do that?
Because you don't know what perspective is.
Yeah, so right and left is an example of a binary thing, right? You've got 2 options, right and left. Would we want to use 1s and 0s with that?
Really?
Why not?
Who's to say which is which?
So this is an arbitrary binary selection. Yeah, there's two. The north and south would be the same thing. Like, yeah, north kind of feels like 1 and south feels like 0, but that's not good enough to program your rocket ship. Right? One of them is going to go to the moon, and one is going to crash into the ocean every time because I wasn't sure which right and left we were talking about or which north and south or whatever. So left and right is a bad example because you might not, dude, left just feels like 0 to me. I agree, but Liam's always got to be different. So he codes it opposite, and now all of a sudden our robot is doing the wrong thing because left and right was, these are kind of the core. Everybody agrees with these ones on the board, but right and left, north and south, you're not going to want to do those with binary. Now, could you represent them? Sure, but you'd want to be really, really precise and exact on which one you're representing with which one. Right? Okay, so how do we write a number so I've got a 4-digit number. In decimal, what's the biggest number we could represent with 4 digits? 9999? Everybody agree? This would be the biggest number we could represent? What about the smallest number?
0.9.
No, 0, 0, 0.
0.0001. Wait.
No,
0.
0.
Is point a digit?
We're not doing decimals. Hold on, hold tight. Decimals
That's
in
not a number. It's
decimals sucks, so let's not think about decimals quite yet. Would we agree this is the smallest number, not including negatives, not including decimals? Is this the smallest number we could represent? We're going to say 0 is a number for the sake of computer science. So, okay, I agree. So using a single digit in decimal, what's the largest digit? What's the largest number we could represent? 9. Smallest number? 0. What about binary? What's the biggest number we can represent with binary?
1.
What's the smallest number?
I mean, 0.
You say represent. We're not representing binary.
Well, we're representing a number of things. A number of M&Ms in our jar with 1 digit in binary. How many M&Ms can we represent? Maximum. Just 1. Right? This is on or off. We can represent 1 M&M with 1 digit. Or we could represent 0, right? We could, if we change that to 0, yep, I ate all of them. No more M&Ms.
And the biggest determine the size of 0.
Let's add another digit. In decimal, just to give us an equivalent here, what's the biggest number we could represent with 2 digits? 99. Just shy of 100 things. 100 M&Ms. We have 99 M&Ms. We could represent how many from 0 M&Ms all the way up to 99 with our 2 digits. We could figure that out. 57, 83, 29, whatever. We could figure that out. What about in binary, though? What's the biggest number of M&Ms we could actually represent?
Test. 1 and 0.
1 and 0 doesn't make 10. 1 and 0 is an off and an on.
1 and 0 makes sense.
Well, we could do either 1 or 2, right? This is 1 M&M. This is 0 M&Ms. How would we represent 2 M&Ms?
That's 11, actually.
Or would it be a 1 or would it be a 0 or 1 and 0? 0 and 1.
So this is the part of binary that is going to trip you up.
11.
Okay? In decimal, what place is this? Ones place. In decimal, what place is this? Tens. Well, we can't do that. Computers don't have 10 fingers like we do. Computers only have 2 fingers? Computers have 2 states, on or off, right? So we don't have 1s and 10s. In binary, we have 1s, and then we have 2s. This is the leap. This is where this gets weird.
Would this still be 1, 1?
Okay, so hold tight, hold tight, hold tight, hold tight. So with 2 decimals, we could represent any number from 0 to 99,
Okay.
right? with 2 binary digits, we can represent significantly less. Because we only now have 2 places. We have a 1's place and a 2's place. So with 2 digits, we've got these numbers that we're going to try to convert from decimal into binary. Well, 0 is kind of easy, right? What's 0? With 2 places. 0, 0. Right? Yeah, so this is the leap, and this is where this gets a little weird. How would we represent 1 with 2 binary digits? What does 0, 1 mean? How many 2's do we have in the number 1? None. How many 1's do we have in the number 1? 1. So how would we represent 2?
1, 0. 1, 0.
Why not 1, 1?
Because that'd be 3.
Now, I want you to think about this. And again, this is the leap. When I see 1, 0, what do I immediately think? What number am I thinking in my mind? 10. I'm thinking 10. It's not 10. It's 1, 0 in binary. And this is the hard part of looking at binary numbers. Wow, it's all 11s and 1s and 111s and 101s and whatever. Yes, you have to divest. This is the decimal number. This is the binary number. So how would we represent 3? 1, 1.
So it's technically the same. How do you do it like 18 digits then?
We're getting there. You gotta grow to that. You know, you've got to pace yourself. You want to immediately jump to an 18-digit binary number? Come on, bro. Well, we're gonna get there. So how do we represent 4 M&Ms with 2 binary digits?
Would it be 1, 1, 0?
Oh, 2, 0. I like it. 2 2's. Why can't a computer do that? Yeah, so a computer doesn't know the number 2.
Yeah.
A computer doesn't have 2 would represent a 0, 1, and a 2. Well, the lights in here are either on or they're off. That's the only 2 states that you get. There's no like half on, half off.
1.
Can we represent, here's the question. Can we represent the decimal number 4 with 2 binary digits?
No.
We cannot.
Are there multiple?
So you're wrong.
We cannot. So just like
1, 0?
if I filled this with M&Ms and I counted them and there's 382 M&Ms in here. If I only had 2 digits, could I tell you how many M&Ms are in here? No, I just wouldn't have enough. I can only get to 99 and then I'm limited out. Binary is the same way, only in smaller pieces.
0, 2, and 1, 1.
So we need to add another digit.
What? Where's the 3's at?
Oh, that makes sense.
Is it just times 2? How's that make sense?
Multiply by 2.
I mean, it makes sense, but why?
Also be like
Well,
1, 0, 0.
in decimal, what do we multiply by on each subsequent
10.
digit? 10. In binary, base 2, we are doubling. Each digit doubles. So what will be the next digit after this? What will be the 4th spot? Would be 8s. So now, how can we represent with 3 digits in binary, how can we represent the number 4?
4, never mind. I was gonna do 2, 1.
Yeah, so that's the trap, right? Is you have to remember in binary, you've only got 2 digits to work with. How would we do 5?
1, 0, 1.
And so on and so forth. Where are we going to run out of digits?
Never.
What's the last number with 3 digits that we can represent?
No, because we have 8. Or, okay.
6, 7, 8. All right, so 6 is going to be
1, 1, 0.
Yo.
a 2 or a 4, a 2, and now we got enough. A 7 is going to be, what about 8?
1, 0, 0, 0.
Yeah, so what do we need to get to 8?
Multiply it again.
We need another digit. And to get another digit in binary, just like we would in decimal, we keep expanding to the left. We'd need another place. What is this going to be? 8s. And so this is where this will keep growing and doubling until you need enough digits to get to whatever number you're trying to represent. So if you have a bigger and bigger jar with more and more M&Ms, you may need 4 binary digits. You may need 8. You may need 24 binary digits, whatever.
Who made this thing?
Computer nerds.
Letters and other things.
Okay, so you're thinking of hexadecimal, which is another different thing that we use in computer science, but we won't get to that. Maybe in this unit, we might.
That can only
Because
represent
like,
numbers.
there's some that come into letters, yeah.
Okay, so yes.
Yeah, and your computer.
So Charlotte, to answer your question,
Yeah.
Just assign 1 through 20.
if we have 3 decimal digits, what's the biggest number of things we can represent?
What do you mean?
3 digits. We have 1, 2, 3 digits. In decimal, in our number system, what's the biggest number? 999. 999. Okay? In hexadecimal, with 3 digits, we can represent 2,000 something things. So hexadecimal has, instead of the 0 through 9, it has 16 different digits in each place. So that's the number 1. We'll get to that.
Billions of those.
Right now we're going backwards. We're going back to, we're going to where we only have 2 digits from 10. Okay? All right, so let's, everybody got at least a cursory grasp of this?
Yeah.
Let's make it weird. Climber, I hear you say. What does this have anything to do with the physics that we've been learning?
Electricity.
To that I say, not a lot, but I'm going to stretch it to make it work.
What?
No, it's okay. You don't have to.
Because they said just
Computer graphics. If I say the word pixel, what am I talking about?
One
movie.
little
A movie. A movie.
Okay, so no, not the movie Pixels. That's, but kind of. What am I talking about if I'm talking about a pixel? One box of a display, a screen or whatever, that will display some light, some color. You can modify the color of a pixel.
It's pretty crazy how this is so small.
Who remembers this from, yesterday?
I don't know what you're talking about.
Yeah.
What's that?
I don't know if
So,
right.
once again, binary is a representation of on or off. If I want to represent the color red, which of these would be on and which of these would be off? If I'm trying to display the color red. Red would be on, right? What about green and blue?
So this is traditional hex RGB values. This is just binary.
No, this is RGB values, but it's only with on or off. So like when you talk about like 16-bit color, every red gets 16 bits, green gets 16 bits, and you get different intensities.
Yeah.
So instead of on or off, you got like half on, half off, whatever. We're just doing on or off because that's what we learned with the thing. All right, what if I want to represent blue?
001.
So this is how, or a way, to explain to a computer, I want you to display a certain color. Right? And the computer only knows on or off, and a computer monitor can display 3 different colors on each pixel. If you like zoom in on a computer screen, you'll see like a little square, and sometimes it's red or blue or green or combinations based on what you're trying to display. So a computer understands this. We're talking in the language of a computer. You don't tell a computer blue. You tell a computer color palette 001. And again, a real monitor has many, many more colors, but we got training wheels on right now. Let's get crazy. How do I represent cyan?
0, 1.
Why 0, 1, 1? How do we do cyan? Green and blue. So we turn both of those on. And we get cyan. What about, let's make this a little smaller, I guess. What about white? Why 1, 1, 1? Yeah, we add all three colors together. What about black then? What's that? I thought you hated this stuff. I thought you were upset today that you had to learn this. And here you are, rocking it. 0, 0, 0. So, how many different colors can we represent with RGB and our 3 bits? How many total different colors? 8. Why 8? Break that down for me.
You got red, green, blue.
Yeah, you got your primary colors, 3 primary colors, 3 secondaries, and then white and black.
Peter, I like that.
So we have a color palette. We have a coding scheme to describe these colors. So all that's left is for us to make some art.
This is kind of getting interesting. The stuff I did in like 7th grade was nothing like this.
No.
What the butt?
Okay, so let's do this. Let's select it. Let's expand it.
Oh?
Okay, so this is pixel art. This is just a selection of, I Googled this, right? And these are 8 by 8. Each of these is an 8 by 8 square. And the color palette here is probably more than we have. Again, most computers aren't limited to just those 8 colors. We're going to limit that for ours. So you all are going to make some kind of pixel art. I don't care what this is. I don't care if you Google this and kind of copy it. You will probably have to adjust the colors to match our palette for most of these. My favorite is the chicken. So your instructions. All right, you're going to want to pay attention to this. Your instructions are to design some kind of 8 by 8 pixel art. It needs to incorporate at least 4 colors, but obviously no more than 8. That's all we have are the 8 that we've listed. Okay, so you have 8 different colors. You have to design something. If you want to be creative and design your own, great. If you want to phone it in and just find some pixel art online, that's fine. Please don't everybody do the chicken. That's the one I'm going to do. I like that there's actually 2 different versions of dragons on here. There's the taller dragon with 3 back scales, and then there's the shorter dragon with 2 back scales but 2 horns. So, and this just gives you an idea of, hey, I want to draw a dragon. Here's 2 different ones with the same constraints that you guys will have. 8 by 8 is the maximum resolution. Each square on your 8 by 8 has to be its own color. So some students earlier were drawing very elaborate drawings, but again, a pixel can only be blue or red or cyan or whatever.
That's gonna be great. Greater than yours.
Okay, that's a great question. So you can use colored stuff to do this, but for this, you just need to represent whatever color is in the box. A lot of students are writing like cyan or blue or just saying Y for yellow or whatever. Sure? But again, that's where we're going to struggle because you don't have 3 shades of
pink, yeah.
Yes. So this is the, well, modify it. It's going to be yours. You get to pick the color palette.
Yeah.
You know, whether you shades or yellow or however you do it is kind of up to you. But you need at least 4 colors in your pixel art.
How do computers make different shades?
Okay, so in a real computer, in a real display, each pixel has RGB,
Right.
but there's an intensity slider.
Oh, right.
You've seen this with the big color wheel that you kind of slide and find different colors. All that's doing is instead of red being on or off, red can be half, and red can be 3/4, and red can be whatever, and blue can be half. And when you mix all those numbers together, you get, and depending on how many digits you allow, is how many different shades you get. So this is the difference between 8-bit color, 64-bit color, 128-bit color. When you ever look at displays on a computer or something, that's a selection. You get to pick how many different shades of each color you get, and that's just more memory, because obviously we can represent red with only 3 different things, 3 different on or offs, right? A computer is going to represent a color with 128 different things.
Color in the black background?
Huh?
Is the black background or color?
So the way this program works, yes, the background is going to be black, but you're going to want to color every pixel. So if you want black, you would do 000 for yes.
Are we actually coloring it or are we writing it?
So for today, I don't care. You're just, whether you list colors in your squares, I just want a representation of one of the 8 colors in each square. That's what you're looking for. Each square needs you can list it. You can do C for cyan. You can do, black and blue is going to be tough. You're going to have to distinguish between black and blue. And then tomorrow, we'll do something with this.
Are you gonna like make it bigger?
Well, we're going to actually transfer it into computer language.